Welcome to our webinar. My name is Pekka Pohjanne and I will be your host through this webinar. And before going to the actual agenda, few practical issues. Duration of the webinar, including a question and answers session, is about 50 minutes. And then question and answers, we will answer all questions at the end of a webinar, and you can submit your questions through the Ask a Question tab. And please note that the tab is not visible if you are in the full screen mode. And then about the presentation slides and the recording, those will be distributed to all within a week after this webinar. And then shortly about today's agenda. We will have 3 scientific technical presentations, and then at the end of this question and answer issues. And when thinking about hydrogen, the hydrogen topic is now booming a lot, and it's a quite huge, broad area, so cooperation is really needed in this context. So seldom or hardly any one can do all by yourself, so cooperation is the key. And then some figures from VTT, basic figures from VTT, if you are not familiar with VTT before. So VTT is one of the leading research organizations in Europe, and our current staff is around 2,200 people. And through science and technology, we are turning global challenges to sustainable solutions to companies and society in a responsible way. And then if we talk about hydrogen economy, there is no doubt that the electrification and hydrogen are key drivers when talking about green energy, green transition. And the main advantage of a hydrogen is that it's versatile. So versatile energy carrier, but also a raw material for different kind of products and chemicals. And at the VTT, we are working throughout the hydrogen value chain, and we are supporting companies and economy throughout the value chain to get a valuable, let's say, good performance solutions. So starting with the hydrogen production, different kind of production, electrolyzers, gasification, so on. And then talking about hydrogen transport and storage issues, pipelines, hydrogen underground, and then not forgetting the use and conversion of a hydrogen. Hydrogen, for example, as a fuel or as a base chemical to produce a power-to-X components, air fuels, together with the carbon dioxide. VTT has versatile and good facilities to examine hydrogen, produce new kind of chemicals, and we will expand our capabilities in future. So we are building a new clean energy pilot platform to Bioruukki, and it should be operational in 2025-26. So innovative platform for hydrogen, electrification, and renewable fuels. And then if you are interested, our first webinar on hydrogen and materials, the presentations and recordings can be downloaded via the link shown below. So please check. And now let's move to our technical presentations. So our first speaker will be Thomas Oehlichsläger, who is a specialist in material science, corrosion engineering, and before joining to VTT 2020, he was working at Outokumpu Stainless, specialized for development of stainless steels. Please, Thomas.
Thank you, Pekka, for this introduction. I will tell you today a little bit about material challenges which are related to future hydrogen and power-to-X processes. we will have green hydrogen. This is coming. This has been decided worldwide. The European Commission, the European Union has a hydrogen strategy. The US has a hydrogen strategy. China. Finland wants to produce 10% of the hydrogen, of the green hydrogen in Europe by 2030. And also countries that are at the moment producing fossil fuel are interested in hydrogen. So this is coming. And what will we do when we have so much green hydrogen with it? First of all, we have to store it. We can do that as liquid hydrogen. Then we have here low temperatures, which is about minus 250 degrees Celsius or even lower. And the pressure is relatively low. And it's also possible to store hydrogen only compressed. That is possible at ambient conditions. And also combination with Korea compressed hydrogen, where we have minus 200, minus 230 degrees Celsius and about up to 1,000 bars. And we get then the highest volumetric energy density. For long-term storages, we can use lined rock caverns, which is possible more here or will be probably more used in Scandinavia. In Central Europe, where we have depleted oil and gas fields, it's possible to store the hydrogen as natural gas is stored at the moment. So the conditions here are also pressurized and at temperatures that are there at the site. It's also possible to store hydrogen as metal hydrides, which is used only in special applications. For instance, on submarines, this could be useful or is used. And it's also possible to absorb hydrogen on high surface materials, or it can be even chemically bonded to chemicals so that the hydrogen is not stored as gas anymore. When we have that hydrogen stored, we also want to transport it to the places where we use it. And we do that, as Pekka already mentioned, with pipelines. They can be new or they can be repurposed existing natural gas pipelines. There will be long-range transport, for instance, in tank ships. Can be done usually as liquefied hydrogen. Then it's also possible to do that when hydrogen is chemically bonded, for instance, to methyl cyclohexane, which is then stripped to toluene. And also there will be local distribution of hydrogen in trains and trucks. When we have that hydrogen distributed to the place where we want to use it, we can do quite a lot of things with it. There will be the possibility to use hydrogen as a fuel for burner, replacing natural gas, for instance, or propane. Then there is the possibility to use hydrogen in combustion engines that may be not useful for cars, or perhaps even that's possible. But maybe that's more with ships or even planes, if that would be possible. Then there are the fuel cells, which are producing electricity from hydrogen. And then there is the possibility to use hydrogen to produce base chemicals for the chemical industry, and also so-called e-fuels, fuels made artificially from hydrogen and a carbon source. E-gasoline, e-diesel, e-kerosene, that is what's on the agenda, but also the base chemicals, ammonia, methane, which is natural gas, hydrocarbons, alcohols, organics, and so on. And it can also be used in metallurgical processes as a reductant. This is at the moment coming more into vogue for the production of iron instead of the reduction by coal to produce direct reduced iron. When we're looking at these industrial processes, when we can use, where we will use green hydrogen, there are these processes, for instance, for ammonia, methane, and also these hydrocarbons and also methanol. That's possible to do at increased temperature with an increased pressure commonly using a catalyst. And the temperature range is usually about 150 to 450 degrees Celsius, and the pressure can be even several hundred bars if needed. As you can see, these processes have their own names, and they were named after their inventors. And if you look at the pictures here below, they are quite old, these pictures. So these processes are quite old. They are about 100 years old. Some of them even, in the beginnings, even a bit older. So there is some experience with these processes. They have been used over the times more or less. And still they are being developed further and adapted to the recent needs and also to new feedstocks. For instance, it was yesterday in the news here in Finland that VTT, that the research project where VTT has contributed, has produced its first batch of e-diesel, and it was tested in a tractor. So with the help of there we had a cooperation with several industrial partners, and it was funded by Business Finland here. So this project here included several steps. It included hydrogen production in a high temperature electrochemical cell. The carbon was captured from a process environment, and then the Fischer-Tropsch synthesis to produce the hydrocarbon. So cooperation is here very essential. To summarize here, where we can encounter hydrogen, we can say it takes place. You can find it from very low cryogenic temperature to very high temperatures, from minus 250 to plus 1,000 degrees. The pressure can be at 1 bar at ambient conditions, or even at high pressures of up to 1,000 bars. So it's a very broad range, and this is a challenge for engineering materials here. And when we have to look what is hydrogen doing with our engineering materials, for instance, with metals here, we often observe that hydrogen is absorbed in metals as hydrogen atoms, and it is incorporated in the metal lattice on interstitial positions. This enables quite often a relative fast diffusion by hopping mechanism between these interstitial sites. And also the hydrogen can interact with the crystal defects, with the dislocation structure here in these metals, and changes by that quite often the mechanical properties of the material. The influence of of course, if it's in the crystal structure itself the crystal structure of the metal itself has an influence how this takes place. Usually, face center cubic metals or metals with the face center cubic crystal structure are less affected than with the body center cubic or a hexagonal closed pack structure. So the FCC structure is austenite, the BCCs in the ion system, the ferrite and the HCP would be martensite. This has a problem because this may cause problems. Hydrogen changes the mechanical properties, and it causes hydrogen embrittlement. This leads often to cracking because the strength of the material is increased and the material loses ductility and impact toughness. The reason here is roughly summarized that the hydrogen interacts with the interstitials, interacts with the dislocation structure and its movement. So this is important, especially when metals are under load or are deformed. On this picture here, on this microscopic picture here, you can see a series of electron microscope images with electron channeling contrast, where you can see actually dislocations moving. The picture here after 72 hours, some dislocations have moved. So this material was also under mechanical load. So this was done this was caused by hydrogen. And when the authors of this study did a similar experiment without mechanical stress, they did not observe this. So this is a clear effect that hydrogen interacts with dislocations in metals. What else can happen? It's possible that we observe blistering when when metals were in contact with hydrogen. Especially high pressure hydrogen bubbles can form inside the metal and cause brittle ruptures and blisters. Usually here the hydrogen pressure outside of the metal has to be lower than inside the metal. There needs to be usually a temperature or pressure gradient. Several metals are affected. A typical example would be blisters in low-strength carbon steels after acid pickling. That is something that sometimes is observed. Another phenomenon is hydrogen attack or hydrogen reaction embrittlement. That takes usually place at higher temperatures. And here the hydrogen reacts chemically with the carbon in the steel, for instance. It can also react with oxygen in copper, and then water would form. For instance, when we have the calcium carbon, there methane forms. When we have here another failure possibility for metals with hydrogen is the formation of hydrides. Metal hydrides may form with hydrogen, and then the material they're usually brittle. They may even be non-metallic, and cause then a degradation of the mechanical properties of the material. Typical examples here are, for instance, magnesium, palladium, and also, for instance, it's discussed with aluminium and nickel. When you look at polymers, the situation is a little bit different. Hydrogen is interacting differently with polymers. It is actually not very reactive gas and does not cause direct chemical degradation of a polymer. It may be that it sometimes reacts with certain additives, but this is a really rare case. It's usually dissolved in the polymer as hydrogen molecules, and especially under high pressure, this can lead to swelling of the polymer, which then changes the mechanical properties of the polymer. For instance, the polymer can be the stiffness of the polymer can increase, or the elongation of elastomers will become even higher when there's hydrogen pressure from the outside. Another situation here is when high pressure hydrogen was in contact with a polymer, it had been dissolved in the polymer, and then the pressure is reduced. The hydrogen can form gas bubbles in the polymer while it's diffusing out of the polymer. And this can cause blisters, it can cause the rupture of the polymer, or even foam can form. And this is not a phenomenon that is only caused by hydrogen. This takes also place, for instance, in high pressure nitrogen or in high pressure methane. That's also possible. The diffusion generally of hydrogen through polymers depends mainly on the properties of the polymer. It's not so much caused by the size of the atom or of the molecule, which is quite small. On the other hand, when there is for instance, a small physical leak, a very, very small physical leak in a seal, Graham's diffusion law comes into action, and which says that the diffusion of gas through a very small hole depends on the molecular mass of the gas. And as hydrogen is a very small molecule, or a very light molecule, the diffusion is quite fast. For instance, it's four times faster than that of methane. That needs to be, for instance, considered when you construct or you plan some ceilings or gaskets. So to summarize my presentation here shortly, if you to reduce the consumption of fossil fuels and fossil raw materials, hydrogen will be used more often in the future than today. This means the processes that use hydrogen will have higher volumes. There will be more installations. There will be more different applications, and there will be also new users. When suitable materials are used, it is possible that hydrogen will be used or can be used safely in these applications because, as you probably already know, hydrogen is an explosive gas and poses some safety risks. When we have these applications, there are really many different conditions where we can encounter hydrogen, as I said before, from low temperatures to very high temperatures, from ambient pressure to very high pressures. And we know quite a lot of these processes, or many processes of these where we will use hydrogen already for a quite long time. There is already quite a lot of experiences with many materials, and still there is some data missing on a lot of materials. Standardization, which is also very important for constructing safe process equipment, is at the moment lagging behind, but there are many efforts done. Then we also have to consider that the manufacturing of an industrial device may influence its behavior in the presence of hydrogen. For instance, welding may affect here, or mechanical deformation and so on. So that needs also to be considered when we choose materials and construct our equipment. So material testing and component testing is therefore quite often necessary for new applications. That's all what I can say here in the short time. Thank you very much.
So thank you, Thomas. And our next speaker is Rami Pohja. His specialty areas are high temperature materials and materials applications in energy applications, especially looking degradation mechanisms and lifetime issues. So please, Rami.
Thank you, Pekka. So this presentation is about process changes and operation in hydrogen economy. Now, in energy production, hydrogen is considered to be a very important element in the transition from fossil fuels to renewable energy sources across these industries. And whether we talk about new plants or older plants converted to hydrogen service, the effective use of hydrogen in industrial processes demands a deep understanding of materials performance in hydrogen environments. Hydrogen can have detrimental effects on materials, as will be illustrated in this presentation through an industrial case example of a degradation mechanism called high-temperature hydrogen attack. Furthermore, this presentation aims to provide some material selection guidance to protect against hydrogen's adverse effects in materials. Then some words about the high-temperature hydrogen attack. High-temperature hydrogen attack is defined as a permanent and irreversible decrease of mechanical properties of a metal or an alloy during exposure to hydrogen at high temperatures. These two main forms of high-temperature hydrogen attack manifestations are firstly this softening, which is associated with surface and material decarburization, and secondly embrittlement, which is associated with internal cavitation and fissuring along the grain boundaries due to these methane bubbles. The high-temperature hydrogen attack mechanism goes as follows. First, the chemical reaction between hydrogen and carbon in solution in steel or carbides in the microstructure of the material form methane. This consumption of carbon in the matrix will promote dissolution of these carbides to keep the atomic carbon in solution in balance. Now these methane molecules are too large to diffuse out of the steel, and therefore they cause significant pressure buildup that will result in the formation of cavities or voids, which are also referred to as methane bubbles at the grain boundaries of the material or other areas of high interfacial energy. And these areas of high interfacial energy can be, for example, inclusion surfaces. Material grade is considered to be very important with regards to process temperature in the hydrogen service. The graph here shows operation limits for different steels in hydrogen service. This work is mainly achievement by G.A. Nelson, so these curves are often referred to as Nelson curves. In the graph, the x-axis stands for hydrogen partial pressure and y-axis stands for temperature. Now, if we look at a single curve here below the particular curve, the combination of temperature and hydrogen pressure form a safe area against high temperature hydrogen attack for that particular material. And above the curve, there is a danger for high temperature hydrogen attack. If we look at the lowest curves, we see that they are plain carbon steel materials welded with or without post-weld heat treatment. And when we go upper in these curves, we see that there are alloying elements such as chromium, molybdenum and vanadium in these steels, which improve their resistance against the high temperature hydrogen attack. Then I'm going to present an industrial case example where an older plant which has been converted to hydrogen service has suffered from severe high temperature hydrogen attack. In this example, circulating gas piping failure had occurred in a process application which involves hydrogen. The pipe that failed in this case was a carbon steel P235GH steel with outer diameter of 114.3 millimeters and with a wall thickness of 12.5 millimeters. The process included hydrogen, methane and carbon monoxide, and the process pressure was up to 116 bars. The temperature was from 330 to 355 degrees Celsius and time elapsed was 11 months. So the pipe failure occurred here after 11 months of use and the pipe had broken into several pieces, so the failure was rather extreme. When we having first look at the samples, it revealed that samples exhibited deposit layer both in the inner and outer surfaces, but no substantial corrosion which would, for example, lead to significant wall thinning had occurred in these samples. Closer visual look revealed that these samples exhibited numerous internal cracks, and these cracks and failure initiated from the inner surface of the pipe going towards the outer surface of the pipe. And if we look at the right-hand side figure here, we can see two quite major cracks initiating from the inner surface going towards the outer surface of the pipe. Also, severe decarburization had occurred from the inner surface almost throughout the pipe thickness, and the hardness values in the decarburized zone were significantly lower than values near the outer surface. So if we look at the image here, we can see a major crack in the middle, but we can also see decreased hardness values from 110 to 130 Vickers in the decarburized zones. Near the outer surface, we can see hardness values which would be typical for this kind of steel in normal conditions, and those are values of about 160 Vickers. The microstructure in the decarburized zone shows decomposition of perlite and voids as well as cracking in the grain boundaries. So if we look at the microstructural image here, we see that all the darker pearlite or binate grains have converted into ferrite, and we can also see numerous cracks in the grain boundaries originally due to the methane bubbles. So based on these investigations made at VTT and also based on the background data from the customer, it was evident that severe high-temperature hydrogen attack had occurred in this carbon steel pipe, which was in an older plant that had been converted into hydrogen service. Now, how to prevent this high-temperature hydrogen attack from happening? Now, materials' susceptibility to decarburization and subsequent high-temperature hydrogen attack is a combined effect of materials' chemical composition, process temperature, and time. With ferritic steels, these carbide-forming elements such as chromium, molybdenum, and vanadium in these steels decrease the susceptibility to high-temperature hydrogen attack because these elements hinder the methane formation. Austenitic stainless steels are better. They exhibit more stable phase-sensile cubic structure against high-temperature hydrogen attack, and their alloying elements contribute to the formation of stable carbides and nitrides, which can help mitigate the effects of hydrogen attack. But in industrial applications, things tend to be far more complicated than relying on these kind of handbook instructions. Therefore, VTT conducts comprehensive research for materials in hydrogen service, and we can provide support for our customers in the unique cases and challenges. So if we think about industrial plant and its life cycle, VTT can offer support for the whole life cycle of a plant, from investment optimization through startup operation, maintenance, to retrofit conversion, and even decommissioning. So we can provide science-based answers to material challenges of our customers, and we can help our customers to utilize the full value of their investment and maximize the overall equipment efficiency and the plant performance. VTT has a wide range of materials experts. We have a solid knowledge on materials technology and materials performance, which is based on high-end scientific research that we carry on at VTT related to these issues. So please do not hesitate to contact us with your interesting material challenges. That is all. Thank you.
Thank you, Rami. And our next speaker is Timo Kinos. So Timo is an expert on material development and material development on different kind of applications. So, for example, he's been looking for high-temperature materials for e-reactors, but also magnetic materials and also electromagnetic shielding. So, please, Timo.
Yeah, thank you, Pekka. So my name is Timo Kinos, and I work in the team called Sustainable Material Design, but this work about e-reactor and its applications, that has been done in close cooperation with our colleagues who are working in gasification and synthetic gas production. Next slide, please. Oh, it's mine. So Power-to-X technologies are words which can be seen and heard today quite often, because they enable this production of carbon-neutral fuels and chemicals, for example, by utilizing green hydrogen and captured carbon dioxide. So we need this renewable energy from solar or wind power, for example, and the hydrogen is produced in electrolyzers instead of cracking, for example, liquid gas, what has been doing now, today even. And then producing this synthesis gas and then use that further in the, for example, in the Fischer-Tropsch synthesis, it's possible to make hydrocarbon products like e-gasoline, e-diesel, and that kind of things. And of course, it's also possible to use electricity directly in the vehicles and also in industry and for heating without this synthesis. So why this actually happens, this kind of transition towards e-fuels and e-chemicals? So currently the main drivers, according to our interviews, are the certificates and regulations and legislation given by the countries and EU, for example. There's also customer demand because customers understand that, hey, we are responsible of our planet and Earth and to make it a more safe place to live. And then, of course, political decisions are there in the background. And subsidies play also important role. And then the price actually is, I think, the most important thing. So this transition doesn't happen in one night. So it will take decades in practice. And according to these interviews, Fischer-Tropsch and electrolyzer technologies, they will be the most preferred e-fuel production in the future. But one important thing is also that these fuels they should be matched with the existing infrastructures and pathways that can replace these fossils directly. Different countries have dealt with different ways to speed up this process. So in EU use a little bit more stick, and US, for example, carrot type of approach to have this transition. But of course, then there's also safety issues in the place and storage of these new fuels. And electrification plays a key role in accelerating the new fuel development. And their sufficiency and stable supply of renewable energy, electricity, is seen maybe a concern that do we have enough of that in the future? So this is one estimation about how fast this transition will happen towards e-fuels and e-chemicals. This is given by the Lappeenranta-Lahti University. And as we can see, it will take, let's say, several decades before we get a bigger amount of e-fuels and e-chemicals. So these normal fossil fuels will stay there in the market quite a long time still, because this will be also a price issues in many cases. These new fuels, they are more expensive than the conventional ones. This is kind of showing that what kind of activities we normally do when we have an idea and try to develop that to a product. So we need to have there, of course, technical verifications and validations, first in laboratory, then in some infrastructure, and then upscaling to a bigger unit. But in same times, we must have also understanding about the markets. So what should be done so that they can be sold, and we must, of course, use also or do kind of patent field studies that, hey, are these patented, these new things somewhere else maybe? And then of course, when we go to a higher level of upscaling, we will need some kind of partners, because industrial validations, they are quite expensive and need a big pocket to pay that. But all this basically can be done at VTT. So about this e-reactor itself. So shortly, it's an electrified, resistively heated element in the reactor. Normally, these reactors have been heated kind of externally using or burning fossil fuels. But now we are heating this critical component directly with an electricity, with the clean electricity, green electricity. So we don't cause any carbon emissions in this process. And this can be now done for the reactions, for example, to Power-to-X and carbon capture utilization. These practical syntheses are, for example, reverse body gas shift reactions. It can be used also to ammonia decomposition and dry and steam reforming in practice. And this element which can be heated and coated with a catalyst, because catalyst is there needed as well. So it is a porous element with a radial flow, and the catalyst is then of course incorporated to the tube matrix or deposited on this porous material. So the applications areas could be, for example, these three. So the syngas production in reverse body gas shift technology, and then the syngas will be used further in Fischer-Tropsch, for example, to make e-fuels. As said, also this ammonia decomposition is one application. So the ammonia will be a kind of storage of this green hydrogen in this case. And then we can have also dry and steam reforming to produce hydrogen. This picture is a little bit not so clear, but it actually tells you how this process goes. So we have this clean energy, renewable energy. Then we produce hydrogen in electrolyzers. And we have also captured carbon dioxide and then using, for example, RVGS synthesis, we get those synthesis gas, which can be then further used at Fischer-Tropsch and upgraded to e-fuels. Then this ammonia case, that's basically shown here. Again, electricity production, and then electrolyzers to make hydrogen, and then Haber-Bosch reaction to make ammonia, which can be used, for example, to fertilizer. It can be also used as a fuel in marine applications, in marine motors. But okay, this hydrogen can also be delivered and used in fuel cells if that is needed. But again, this ammonia cracking, that could happen again in our e-reactor device. So we have considered that this kind of value chain could be one option to utilize this ammonia. So option A could be that we use that in ocean vessels, and major flow would be the combustion of this ammonia, but the minor flow would be this kind of hydrogen that could happen as a pilot fuel, because they will need this kind of pilot fuel, those motors. And that kind of hydrogen decomposition could happen locally in the vessel by this e-reactor. So e-reactor kind of replaces this conventional fixed bed cracking systems. And then this dry and steam reforming case. So natural gas is typically used to make hydrogen from the gas. But in this case, again, we can do this reforming in our reactor instead of burning fossil fuels for the heating up the reactor, and then use that again to produce clean and pure hydrogen. So these are so we have started the testing, let's say, a couple of years ago, and these are the very first test results using very simple reactor type, as you can see in the picture. But we could get this quite high carbon dioxide conversion, which the measured value was 61 when the theoretical value at this temperature and pressure would be 65%. So it's quite high value what we actually achieved here. And the efficiency was about 85% regarding of the power usage. A little bit lower if we take into account also the heating up of this nitrogen carrier gas. But it looks very promising, and now we are currently making a little bit bigger reactor and using higher pressures to get better mass transfer values. So if we look at the benefits of this reactor, so we get rid of the combusting these fossil fuels. So we are now directly heating up the critical element with the electricity. So there won't be any kind of carbon dioxide emissions in this type of reactor. Its size is very compact because of this heating type, and the dynamic operation is quite flexible and fast. So faster temperature response and faster startup and shutdown. Efficient productivity. And of course, then the catalyst should be selected correctly so that the reactions take place in effective way. So very kind of promising results. If you think about capex and opex values, here, for example, in case of capex, if we are comparing E-reactor with the traditional external heated RVGS reactor, in case of our reactor, we get 30% capex due to higher gas recycling rate and thus smaller electrolyzer capacity required. And capex, if we then verify or compare E-reactor capex to COSOEC, that's a solid oxide high temperature electrolyzer. So our capex is estimated to be 45% lower based on today's SOEC investment cost. And then about operating expenses concerning technology investment, so jet fuel, for example, produced by this electrolyzer plus Fischer-Tropsch reactions. So OPEX of this E-reactor is about 30 degrees smaller due to higher gas recycling rate. And OPEX of E-reactor versus COSOEC, so they are about the similar level, so no big differences in that. So still summarizing the kind of material technology side very shortly. So we have the catalyzed heated porous element, which can be manufactured, for example, using powder metallurgical methods. And then this catalyst selection is very important, so that reactions happens as they should be. But what we have found in our case, that for example, this reactor type suppresses the carbon formation on the surface of this reactor. That's a very positive thing, of course. But normally this kind of vessel, this is a pressure vessel, our current reactor type, and that is constructed from stainless steel to minimize the risk of hydrogen embrittlement and corrosion. So nothing kind of special things here. This figure here shows that there's plenty of different kind of technologies to make porous materials, but in our case we need an open cell structures, and we have used some of those technologies, for example, to make our element for the reactor. And these are scanning electron-microphone images about those porous materials, what we have manufactured to our reactor, and you can see that actual surface area is in practice quite huge because of this porosity. And it's still big enough so that the gas flow through these walls from in to outside. And my last slide is about the services what VTT can offer to help to identify and drive decarbonization opportunities through Power-to-X, hydrogen economy, and carbon capture utilization concepts and technologies. So we help industries to reduce these emissions and save resources by assessing, modeling, and simulating new concepts, processes, and technologies. We provide analysis and cost-efficient solutions for decarbonization through electrification of carbon-neutral energy carriers, improving processes to emit less carbon dioxide or utilizing carbon dioxide for new products, as in this case, what I just told you. And we solve also technical challenges in relation to hydrogen production, storage, and utilization, and for example, for the material technologies, so that we select the right materials to right place when working with hydrogen. Thank you. That's all from my side.
So thank you, Timo. And these three presentations showed good examples that hydrogen is a promising solution, and one way to tackle these, let's say, green energy transition challenges. But it has also some questions to be answered and some technical issues also, as we had during the last presentation. But those are possible to tackle. So now it's time to move the question and answer section. So please submit your questions through the Ask a Question tab. And we will answer the questions as much as we possible during this webinar. And if not possible to answer due to time limitations to all, we will answer them later on. So, okay. Okay, here's one question to Thomas about hydrogen embrittlement and stainless steel. So, can you elaborate a bit when is that considered an issue and how does it restrict the use of stainless steel? So, hydrogen embrittlement and stainless steels.
Hydrogen embrittlement and stainless steels is mostly related to ferritic or to martensitic stainless steels. Austenitic stainless steels are relatively resistant to hydrogen embrittlement compared to the other to the other steel phases. So when you have the occurrence of martensite, for instance, during deformation of an austenitic stainless steel, you can have a higher tendency for hydrogen embrittlement to occur. And so you need, of course, hydrogen environment, a temperature that's high enough. When you have, for instance, really low temperatures below -100 degrees Celsius, it is commonly not that easy for hydrogen to diffuse into the stainless steel or into metal in general. And then you need also sufficiently high pressure. And this depends on the conditions of your process. So that has to be considered case by case.
Okay, thank you, Thomas. And then a targeted question to Rami. You were talking about Nelson curves. And in which kind of cases do you think that Nelson curve is not enough to evaluate the high temperature hydrogen attack issue?
Well, I would say so that industrial applications are quite complex and they have many kind of sub-issues to consider. So I wouldn't solely rely on these curves. I would strongly recommend to contact a research institute like VTT with these kind of issues, because it can be even dangerous to rely solely on these curves.
Okay, thanks, Rami. And then a direct continuation to that. Thomas, you mentioned that there is still a data missing about hydrogen and material interactions. And how you are tackling these kind of questions?
This is the data is missing. The data is not missing, or is not that much missing, from materials that are actually used. If you look on the data of material compatibility with hydrogen, they had been studied mainly for the materials that are most interesting for these applications. But if you go beyond and looking for new materials that are being developed, then it may be that the data for new materials are missing. And also, it depends on the application and the materials you use there. But if you look at the catalogs and on the material tables regarding hydrogen, most are based on work by NASA, actually. There are some material groups missing, and there could be done more, and more materials could be used with hydrogen. So there are some possibilities still in the material, in the use of materials in hydrogen, but for most applications, materials are already known quite well.
Okay. Is then one issue about repurposing?
Okay. If you look at for instance, at a gas grid that had been built for natural gas and will be then repurposed for hydrogen. That is at the moment going on partly already, or is being planned. And usually the gas grids for natural gas, they are built of carbon steels, and in many cases the compatibility with hydrogen is where the pressure is still in the normal range and so on, is expected to be quite good. But you have also to look at sealing materials, at pumps and other infrastructure in your gas grid. So you have to look what materials are there, and then you can do that. If you look at cryogenic temperatures, where also liquefied nitrogen gas is stored, it's not necessarily that all tanks for cryogenic storage of natural gas are compatible with hydrogen, because for liquefied natural gas, steels with high nickel alloying are used quite often, and these are not compatible with hydrogen. So if your tank for liquefied natural gas would be made of stainless steel, the chances to use that tank also for hydrogen would be higher, but it would be absolutely needed to check that carefully.
Okay, thanks, Thomas. And then I'm looking the watch, so we have 2 minutes maybe left, maybe one limit. So one more general question to Rami. What are the characterization methods used in failure analysis? Can you elaborate a little bit?
Yeah, we usually use a whole lot of different methods in order to get as specific and wide range of information as possible. For example, in this kind of high temperature hydrogen attack case, you can use hardness measurements to see the signs of decarburization. Then, of course, microscopy, scanning electron microscopy, optical microscopy, they are important. Of course, we use also visual inspection, many kind of research methods that help us to find out the root cause of the failure.
Okay, thank you, Rami. And we are now running out of the time, so so we have to end our webinar. And before ending, here is one general question about the presentations. So will the presentations be sent to the attendees? Yes, the presentations and the recording from this webinar will be sent to all attendees, let's say within a week after this webinar. So no problem in that. And also these are available also in a later stage via web, like the presentations from the first webinar. So no problem in that case. And if you have any more specific questions, so you can always take contact to VTT, our presenters, and then we have also a in the final slide we will show soon is a questionnaire about this webinar, so you can think, what do you think, what were the most important issues that you noticed, or what we were missing from this webinar, and if you have any specific questions later on, you can send mail also to Mika Malkamäki, our solutions sales lead in the materials and hydrogen issues. But now we have to end this webinar, and I'll thank all attendees, and I hope that this webinar has been useful to all of you. Thank you.